Um, okay, so the first cut is for x anywhere up to before this downward force of 15,000. Um, so we can treat that distributed load as acting at x over 2. Um, that downward force is 4905x. And so the forces are, you have the 10,000 up, the downward force of 4905x, then you have tension and shear force. And so you get tension equals 0, shear force is this linear function. And then the bending moment, so add up all the moments, and I'm going to calculate it, like always, about this left endpoint. So you have the bending moment minus v times x minus 4905x times x over 2. And so you get bending moment is equal to, and notice this is something that's always going to happen whenever you have squared terms in your bending moments. You're going to have two squared terms that partially cancel. And that has the effect of, remember what I said about the derivative of the bending moment with respect to x is equal to the shear force, right? That subtraction is always necessary in order for that to work out, because when you take the derivative of something squared, you divide the constant by 2, right? So anyways, so we get this negative 4905 plus half of that, and we end up with the bending moment is equal to negative 2542 x squared plus 10,000 x. Anyone get anything different than that they like? Okay, and then the second cut. Now we have to, now we're dealing with x anywhere from that downward force of 15,000 to the endpoint, not including the two endpoints of that interval. So our forces are 10,000 up, 4905x down. Now we also have that 15,000 Newton force down, and then tension, shear force, bending moment. So here are the forces: 10,000, 15,000 down, 4905x down, tension, shear force. And for the moments about the left endpoint, we have the bending moment minus 4905x times x over 2 minus 15,000 times moment arm of 0.5 minus the shear force times the moment arm of x. So you get a tension of 0, a shear force is this linear function. And then your bending moment, again, you get that subtraction of squared terms, and you end up with the bending moment is negative 2452.5x squared minus 5095x plus 7547.5. And these are the diagrams that you get. So no tension anywhere. Shear force, what causes this jump? Yeah, you get a jump of 15,095 caused by that point force of 15,095. And then you have a bending moment that has, it's a quadratic function. It's concave down going up to this point. Then there's that, it's continuous, but it's not differentiable at that point, right? You get that jump in slopes, and you get another concave down quadratic function going back down to 0. And does it make sense that the bending moment is 0 at the two endpoints? And why should it be 0 at the two endpoints? No couple there. No couple at either endpoint. So really, most of the time, like the most likely time that you would have non-zero values for the bending moment at the endpoints is because you have some kind of cantilever or some fixed joint at the endpoints. Okay. All right. So the next one we have to do, well, we could go in any order, but I think the second easiest one is this vertical member. But in order to do that, we're going to have to think a little bit. So now we're going to do the vertical member. Member 1. And this has a horizontal, well, let's rotate it first. So this is pretty easy to rotate. I don't think there's any reason we have to use a rotation matrix. But if we were trying to rotate if we were going to use a rotation matrix, what is the angle that we would want to rotate our original coordinate system to represent this? We'd want, so our coordinate system is like this, right? We want it to be like this with the x-axis pointing down, right? So it's negative 90 degrees, okay? So yeah, it's a very common thing for people to get these backwards because it's a lot more natural to think of rotating the member into the right position. But remember that what we're doing is really rotating the coordinate system into the right orientation, okay? So it's negative 90 degrees is what we want. So you could do this by multiplying all these vectors by cosine negative 90, sine negative 90, sine negative 90, cosine negative 90. But in this case, since it's a 90-degree rotation, you can eyeball it without too much trouble. So I rotated it to have that force of 8468 on the left. So you have a force of 8468.36. Then at the midpoint, you have a force of 15,095 pointing to the left. And then at the end, you have a force to the right of 1721.64. And the distributed load is acting along the length and has a magnitude of 4905 newtons per meter. Okay, so each cut that we do, we're going to treat the distributed load as a point force, right? That's what we've always done with distributed loads, and that's still what we're going to do. So the question is, where do we put the distributed load, right? And I mean, I guess also the magnitude, what's the magnitude and direction of that distributed load? But that one's pretty obvious, okay? We're going to express it as a function of x, and that one isn't too different from a vertical distributed load. But what is different is where do we put the point force, okay? So horizontal distributed loads. So inside each free body diagram, we're going to treat it as a point force. And the question is, where do we put it? Where is it applied? Well, there are two components to its position, right? So let's think about what's relevant to us. So we'll break up the position into horizontal and vertical components. Okay, so what about the horizontal position? So say we have some body like this. Where are we going to locate this force along here? And the answer to that comes from, why do we care? Why do we care at all where this is positioned? Like, where does it matter? What equations does it even come into? Why couldn't we locate it in space somewhere? Yeah, it only matters for the moment. And so think about the moment produced about like this point as you move the force here or here or here. Okay? What effect does it have moving that horizontal force around? It doesn't have any, right? We know that we know you're allowed to move a force along its line of action without changing anything about what it produces, right? We do that whenever it's convenient. So moving a force along its line of action is okay. So this doesn't matter. Okay, so the next question is, where do we locate it vertically? And that really has to do with what's causing the distributed load. So, well, what's causing the distributed load? If it's being caused by some kind of traction, some kind of force along the surface of the beam, then we're going to want to position it along the surface of the beam, you know? And if we're trying to be really precise and the surface of the beam is 4 centimeters from where we're calculating our moments, right? Then the vertical position is 4 centimeters above or below you know what I mean? In most cases, since these beams are way longer than they are thick, it's pretty reasonable to neglect that, but I think it's good to know how you would do it if you wanted to be exact. So if it's a force at the surface, then just position it at the surface. If, like in our case, it's a weight force, then where does that weight act? Yeah, right along the center. So position at the long axis, you know, the center. Yeah, and that's...
Technically, it could be distributed that way too, right?
Oh, uh, yes, you're right about that. So we're not, yeah, you're right. You're exactly right. So if we're doing this for some crazy shaped beam, then yeah, you have to, uh, then you'd have to worry about that. Um, so yeah, that's a good point. Let me change that to centroid. But for the problems we're going to do, it's just going to be along the long axis of the beam. Okay. Okay. So that's all we have to do. And when you think about it that way, uh, these are actually easier to calculate than vertical distributed loads because we don't have to worry about finding the centroid of some shape, you know, because the centroid of the shape would would be used to give us that horizontal position, and that doesn't even matter. Okay. So next time I'll do this one, and then you and groups will combine the vertical and horizontal and do that hard one. Okay.